Hello and welcome back with another interesting problem of TIFR 2018. This is problem number 7 from part B, where we are interested to find out the cardinality of the set A, which is a collection of all continuous functions, not only continuous but non-negative continuous functions defined over 0 to 1, which is satisfying this inequality, that is if we integrate over it from 0 to x, where x can be anything between 0 to 1, that integration will be bigger than or equals to the function itself. Now there are four options are given that and also this inequality is true for all x belongs to 0 and 1. Now observe that there is a spoiler that this statement for all x belong to 0 and 1 is going to play a very crucial role at the end. Now, although there are four options are given, option A says the cardinality of A will be equals to 1. Option B says it will be equals to 2. Option C says it will be equal to infinite. And option D says it will be equal to 0. Now, which of the following is true? Now, we will definitely find that out, and I will request you to give that a try. You can pause this video and try the problem. Okay, great. Now, if you have give them a try, I must say that you not only have enjoyed solving the problem, but you also love the way of thinking about it. Okay, now let me proceed in my way. Now, since the function has been said to be non-negative, that is, the range of it is varying from 0 to infinite, this is clear that this function will be looking something like this. My intention to say is this function will not go down to the x-axis. It will always above the x-axis. Now, this is our 1 and this is 0, and x can be somewhere between 0 and 1. It can be somewhere here. Now, what does this in the left hand side of this inequality mean? That is, there's 0 and x, f of t dt. So here is our f is given. Now, simply in very simpler words, this integration means nothing but the area under the curve, that is up to this much. And I'm not going here. This is not allowed to be taken, but only till the boundary of x. We are allowed to take this. Okay, great. Now, one thing, that is in between 0 to x. So, in 0 to x, I'm sorry. In the interval 0 to x, there exists a point such that it attains the maximum of it, of the function. Suppose here this point is here, and this is our f max. Now, observe another fact. That is, if we consider this rectangle whose height is f max and length is x, now we will try to establish one inequality over here, such that x multiplied with f max of x is always bigger than the integral over 0 to x ft dt. Please pause and justify whether this statement is true or not. Okay, now you can see if I take the right hand side, it is the entire box, the entire this green dotted box. But if we take this right hand side, I'm sorry, this should be the left hand side. So if we take this right hand side, it is only the area below this pink curve. Now clearly this box is obviously bigger than the area under the pink curve. So that is why this is always bigger than this one. And inequality may hold if the function is inequality will hold if the function is a constant function. That is, it's a flat line like this. In that case, in both the cases, the area under the in the both sides, it will be just the area of the rectangle, nothing else. Okay. Now observe one more thing. That is, since x is belonging to 0 and 1, x multiplied with f max is actually less than or equal to f of the f max. Because we know that if we multiply some number which is less than 1, it actually reduces the original number. So since there is also we have 1 and f can also be 0, we can use the inequality, we can use the equal sign. So we will take this into account and plug this into over here, and from that we will get f max will be bigger than or equals to 0 to x f of t dt. Now instead of f max, I'm writing it as f of a is bigger than 0 to x ft dt, where f of a, there is no other reason to write f of a. F of a is nothing but the f max. So why I'm introducing this one another variable is because to rewrite this statement. That is, this statement says that this is true for all x belongs to 0 and 1. But from here we find from this little guy, we have found that there exist a point A in 0 to 1 for which f of x is not less than 0 to x f of t dt. In easier words, if there was if this equality sign was absent in this expression, then this statement would be false. But since there is another option of equality, we must say that when it comes for the question of for all x belongs to 0 and 1, this should be equals to 0. I'm sorry, this both the two sides will be equal. So f of x is equals to integration over 0 to x f of x ft dt. I'm sorry, because only the equality holds. In the statement of the question, we had two options: one, the inequality, and the equality. Both can hold. But by deducing and by all these arguments we had so far, we come to an conclusion that this inequality will not hold. That is, this one. That is this one. This one will not hold, but there is no problem with equality, and this will only hold in case of when f of x is equals to 0. From this we can directly come to this conclusion that this inequality holds if and only if f of x equals to 0. So from that we can conclude on one thing, that is, there exist, from this we can say that there exists only one function f from 0 to 1 to 0 to infinity, for which and that is f of x equals to 0. Now again I'm writing this inequality because although the bigger this sign won't work, but still it is quite nearby to this expression, so I'm just writing it, although only the equality will hold, not the inequality. But still, for there is only one function which is nearby to this statement, and that is our f of x equals to 0. Therefore, there is only one function and the cardinality of a is 1. Hence, option A is correct, where f of x equals to 0. And this is how the problem is. Very simple, very intuitive, and I hope everyone has enjoyed thinking about the problem. Thank you.